Okay, good morning everyone. I hope your heads aren't in too bad shape and you're reasonably sprightly because there's a fair bit in here and I'll try not to hurt your brains too much. As Jason mentioned, I work for a company called Fastly. I'm a senior principal engineer there and at the moment focused on reinvigorating our observability culture and tooling and how we manage our infrastructure. So a lot of you probably are wondering, what is Fastly? It's probably not a technical company that comes readily to mind. You may be a customer, thank you if you are. But if you happen to be reading articles on The Guardian or on the New York Times, or if you happen to use GitHub, if anyone here might happen to use GitHub, or if you're killing time on Reddit, that's coming off our infrastructure. Our infrastructure spans the globe. We have 51 points of presence globally, point of presence being an individual data center with our infrastructure in it. And we have over 22 terabits of connected network transit. So we can take a lot of traffic and we support a whole lot of customers. So you can imagine with an infrastructure this large and the amount of responsibility we have to all of our customers and keeping them online, monitoring is absolutely crucial part of our business. Now, going back to June this year, my partner on this project, Peter Borgon, gave a presentation which he called Observability, the Hard Parts. And one thing I'd really like to kind of get across in this presentation is that if you are having difficulties with monitoring and you have, like everyone has various kinds of Frankenstacks for doing their monitoring, the people are so much more important, like the actual process, the whole system of how the users consume the metrics, how metrics are generated, how engineers interact with the system is just as important as the actual choice of the technical stack together. And if you don't get those two parts working in concert with each other, you're not going to have a successful time. So Peter's talked about, as part of this migration project, we wanted to reboot what the monitoring culture was like within Etsy, within Fastly and within our organization. So yeah, Peter's talk talks a lot about the human side of this project, so I strongly encourage you to watch that at some point. So given that, I'm redubbing this talk Observability, the Easy Parts, because it's just a small matter of programming to do change over the technical stack, but we'll see how that is. So to set the scene, how are we monitoring at Fastly originally? So Fastly's been around for roughly 7 years, starting around 2011. And as you can imagine, the landscape of monitoring tools available in 2011 was relatively limited. We'd settled on and deployed Ganglia early on. Ganglia is an RRD tool-based monitoring system, originally designed for high-performance computing clusters, so the notion of many grids of very homogeneous systems. So that's a pretty good fit for our sort of deployment model, because each individual POP that we have has our caching infrastructure and various things, and they all essentially look the same. So this model of each cluster is a different data center fit really well. And for alerting, we were using Icinga, and we'll talk a bit more about that in a sec. But over the years, we experienced a lot of growing pains with Ganglia. So there's significant operational overhead as you would start to grow out your infrastructure. So Ganglia operates on a sort of centralized aggregator model, that sort of monolithic collection structure that you would see with Graphite and with other systems. So as we would roll out more infrastructure, more of those machines are throwing metrics at this individual aggregator. So over time, we're having to increase capacity of this very small collection of aggregators that were supporting the whole infrastructure. And Ganglia itself isn't that observable. So when you would run into performance issues with Ganglia, it was a pretty interesting challenge to try and figure out what was going wrong. You're dealing with UDP and XML and all of these custom protocols. So it was very hard to kind of actually figure out what was going wrong when it was going wrong. Being based on RRD, we had limited graphing options. So by default, your graphs are rendering at sort of just rendering averages. You can get a min, you can get a max, but if you wanted to do any more complex graphing of your raw metrics, it was very difficult. There was no native alerting support. So for us to bolt on Icinga support, we had to build all of this additional machinery. And you had this sort of disconnect between the metrics being collected and how the alerts were firing. So an alert would fire and you couldn't easily get back to the metric that produced that alert. And then as we got further into things and started increasing our usage of our operational metrics, there was no real API for consuming those metrics. So it was a bit of a black box. So our data science teams and capacity planning teams struggled to get useful operational metrics out of Ganglia itself. So about I would say probably 2014, 2015, some frustrated engineers decided, okay, let's fix this problem. Let's roll out a new system. because obviously the problem is ganglia, not anything else. So we moved on to a software as a service provided, proceeded to try to move on to a software as a service provided metrics collection service. And this was a project that focused on let's just shift tools and hadn't thought too much about the actual processes behind. And the net effect of that is we just doubled our growing pains. Now we're supporting 2 systems. So it becomes a challenge of where do I put my metrics? So if I'm deploying a new system, do I have to add ganglia instrumentation? Do I need to add instrumentation for the third-party vendor? Do I have to do both? If I'm consuming those metrics, which system do I look at to find my metrics? And you would go looking, and it's like, it's not here, is it over here? It was very frustrating, and even naming discrepancies made it very frustrating to use. And we were still in this sort of methodology of writing external plugins and agents. So if you needed to instrument your application, typically you would treat that as a post-release phase. So we've shipped our service, now we're going to instrument it. And that ends up about as well as we're going to write the documentation later. You would have scenarios where services get deployed and there is no monitoring for it. And the people writing the monitoring didn't write the software, so it's hard for them to decide what are the important metrics to cover and how do I know this service is healthy? So again, that sort of comes back to the cultural aspect of it all. But the sort of underlying problem that we had as our infrastructure was scaling horizontally, we're building out more POPs around the world, is that both of these monitoring systems could only really be scaled vertically. So in the ganglia case, we were needing to just keep re-upping the machine. We need faster NICs, we need more CPU, we need more disk I/O, and this was a kind of a constant process. And then with our SaaS vendor, as we wanted to do more with it, it's more hosts being reported in, it's more custom metrics, and the operational cost really starts to impact what we can do. We have to limit what we can do because we have a finite budget that we can spend on monitoring. So we now have 2 monitoring systems. Let's roll out a third, because how bad can that be? But this time round, we were going to sort of look at the whole system, so the humans and the infrastructure. And before we started that, we sort of set down what are our goals? Like, what do we want to achieve rolling out a third monitoring system? So on the operational side, we wanted to make sure that we could roll out a system that would scale with our infrastructure growth. There's no slowing down of Fastly's sort of global footprint, so we're adding more services, adding more systems, adding more data centers. So we need a monitoring system that is sympathetic to that. It needs to be easy to deploy and operate. So ganglia was becoming quite unwieldy to manage at our scale. So whatever new system we chose, we wanted to make sure that it could be easily deployed, and the folks that were operating it and writing instrumentation to be consumed by it, it was easy for them to do their job. We wanted engineering-friendly instrumentation libraries. So culturally, we wanted to move away from this, adding monitoring at the end, to having white box monitoring built in as part of the development process. So the engineers writing the code are also writing the instrumentation that describes and exposes to consumers of that what the important aspects of the software are when it's operating. And then we wanted also first-class API support. So we didn't want to have a system where all the data is locked up. We want to be able to support all the different emerging use cases. And so it needed to provide a modern API for us to be able to do that. And lastly, coming back to that, the original point is we really wanted to kind of use this as an opportunity to reboot our monitoring culture. So given all that, what do we do? So SaaS is ruled out. So that rules out a bunch of vendors doing some amazing stuff that's not really going to work for us. Most of the sort of more modern sort of on-prem monitoring systems that you have still have this kind of centralized model where it's this monolithic collection system where all of your machines are pushing to a single central system. Those systems now support clustering and support sharding and support sort of a more horizontal scaling, but they didn't pass the is it easy to operate test. So anyone who's ever deployed Graphite can probably attest to that if you have to move beyond single Graphite servers. And what that ended up leaving us to, because our solution set was very narrowed at this point, was this little thing called Prometheus. So Peter, who I mentioned earlier on in this project, originally worked at SoundCloud. And at SoundCloud, which is where sort of Prometheus originated, he'd been one of the very early customers in the early development of it, and he recommended we should take a look at it. It's now sort of an open source project. It had just been adopted by the CNCF. And it looked like a really great opportunity to sort of kick the tires, and his experiences with that were really positive. So I did a little bit of research and found, oh, I can grab this single binary off the website and run it on my laptop. And it's like, hang on a second, I just started a binary, and I now have this monitoring system running. I didn't have to write storage schemas. I didn't have to figure out what Cairo libraries I need in Python or all the other dependencies I might need for other systems. One binary, turn it on, off we go. So the initial experience from a first impressions point of view was really, really positive. So we figured, well, let's give that a go. This seems like it could be a good fit. It certainly passes the easy to operate test. So how did we get started doing this project? So the first thing we need to do was build a proof of concept. So we'd done some exploratory testing, it all looks kind of good. What does it look like with real data, real machines on our real infrastructure? So we took what's known as a traceability approach, where rather than building a proof of concept in a really quick and scrappy and throwaway way, we'll build a very small scale version, but build it with all of the sort of production rigor that you would for a full-blown production system. So we're writing proper chef cookbooks to deploy it and having it tied into all of our existing systems. So if the proof of concept was successful, it would be very easy to deploy to our whole infrastructure. The second part was finding a pilot team within the company that was enthusiastic about what we were trying to do. And this pilot team was absolutely crucial to the success of the project in that they were the early adopters. We would pair with them, we would sit with them and figure out together, collaboratively, like how do we instrument your applications? This is what we consider to be best practices around building dashboards and setting up alerting and things like that. So really using that engineering team as a lever for getting sort of more excitement and adoption going on within the company around this project. Once we got them up and running on our proof of concept, we'd iterate through the rest of the service teams. So we have around about 180 engineers at Fastly and dozens of service teams. Each service team has their own separate stack, and some of them are all using different languages. So we'd work our way through all of the teams within Fastly to get everything dialed in. We'd run both systems in parallel, validate that the data going into both, that it all looks consistent, alerts are firing out of both systems, and then we would progress with decommissioning the old systems. So we're kind of partially in the decommissioning stage now. Project's still ongoing. We're about sort of 70 or 80% done. Okay, breathing time. I'm sorry, people, for your hangovers and my Australian accent. Okay, so now that we've kind of established what we need to do, how do we build it? So what does the infrastructure build out look like for Prometheus at Fastly? So if we take our San Jose POP as our first example, so in each one of our POPs, we deploy a pair of Prometheus instances. One of the nice properties of Prometheus is that it's completely shed nothing. There's no clustering, there's no state between multiple machines. If you want HA, you run two of them, and both of those machines do exactly the same thing. Each of those Prometheus instances scrape all of the devices that live within a POP. So our servers, switches, PDUs, you name it. And one thing to call out with Prometheus that's sort of slightly different than a lot of other monitoring systems is it's pool-based. So what Prometheus does is it has a list of all of the what are known as targets on machines, and it makes HTTP requests to them to collect and gather the metrics. So that happens across all of the devices within a POP. And both those machines are just scraping the same, so it's just doubling the scrape traffic within a POP. Now that we have this sort of deployment unit, we can extrapolate that across our entire infrastructure. So each individual POP, each one of those 51 POPs, gets exactly the same topology. So Chef's able to roll out for us a pair of Prometheus instances wherever they need them. And they all just do the same thing. They scrape the devices within a POP. The third component in the infrastructure is what we call the front end. So the front end runs in Google Cloud Platform, and it's the way that all engineers at Fastly interact with our Prometheus infrastructure. So rather than querying directly to these individual instances separately, we have in GCP a few components. So we have Nginx running as a reverse proxy and router. So using separate URI paths, you can route to any one of the Prometheus instances in the infrastructure. We also run Grafana for all of our dashboarding. And that we have each of these Prometheus pairs are wired up as individual data sources within Grafana. And then we also run Federation and Alert Manager, which are two other components of Prometheus. But I'm not going to go into details there because that's like a whole nother talk. One other interesting aspect of Fastly's architecture is that we don't really have a corporate back-end network. So a lot of you are probably running your own data centers, numbers of them. You might have VPN links between them. You can sort of trust transit between them all. Our backend network is the internet. So for us to query our Prometheus instances around the world from our front end in GCP, we have to do it across the internet. So that needs to be secured. So in the spirit of sort of Prometheus's design model is that it doesn't support anything fancy out of the box. It's sort of a composable unit, like a small sharp tool. So we had to build a way for doing authenticated TLS transit across the internet to all of our Prometheus instances. So what does the software stack on a Prometheus server itself look like? So this is one of our A and B pairs within a data center. So for that TLS component I just talked about, we use a thing called Ghost Tunnel. So Ghost Tunnel is a software project that came out of Square. That's a mutually authenticated TLS proxy. So if you have any service that runs on a machine and you need to add TLS authentication to it without having to modify the source, you can run this in front of it. It's super lightweight. We absolutely love it. We use it all over the place now for all kinds of purposes. The second component is our service discovery sidecar. So the way that Fastly's network's architected, we had a need to build a service discovery system, and I'll talk about that in a lot more detail in a minute. The third part is our rules loader. So Prometheus has a bunch of functionality around recording rules, which allow you to run essentially scheduled queries that can produce new time series, allowing you to do summaries and aggregations of very sort of high cardinality metrics. And also the alerting rules run on every single Prometheus instance. So we practice GitOps. All the engineers at Fastly are empowered to be able to write their own recording rules and write their own alerting rules. When they're merged to master, our rules loading process on the servers will fetch those rules. Sort of within a minute, they'll pick it up using something very high tech called cron. And then the last component, of course, is Prometheus. On the server side, so a device within a POP that's instrumented, the stack is super simple. We have our exporters. So an exporter is, in Prometheus terms, is a HTTP endpoint that, when queried, will return in plain text all of the metrics for that particular service. So for things like our daemons that are written in Go, and also some of our C daemons now, they directly expose metrics. So there'll be a TCP port we can hit on a running service that will give you all of the internal metrics of that service. For services that we can't do that or use the client libraries, we run a sidecar. So similar to that agent model, you can run another process alongside the service that collects metrics in some fashion and exposes them in Prometheus format. And then the last component on every service is the service discovery proxy, and we'll get into that now. All right. So, why on earth would you want to build your own service discovery? Prometheus out of the box supports, I think it's around about 14 different service discovery mechanisms. So if you're running Kubernetes, out of the box, Prometheus can discover all of your pods and containers and the whole topology of your cluster by doing nothing more than just running a Prometheus instance in the cluster. Similarly, GCP and AWS, there's a plethora of different mechanisms for service discovery that tie in with what most people these days are running, who are running sort of cloud-native-ish architectures. The catch for us is that all of our infrastructure is bare metal. So we totally embrace the 90s, we're pixie booting, we're running machines in data centers. So we don't have any of these cloud conveniences, which is a little bit of a misnomer. We do have some of these cloud conveniences. We have our own configuration systems and our own APIs, but they're ours. So Prometheus doesn't support them because it doesn't know about them. So we needed to build a mechanism to be able to do service discovery, because we didn't want to have to go back to that Nagios world when you're in this pool-based model and you have to predefine everything that exists in the infrastructure rather than it phoning home to you. So what were the requirements if we were going to build a service discovery mechanism? We wanted the automatic discovery of targets. So when new devices are rolled into POPs, or we turn up a new POP, we don't want to have to manually go and have to configure anything. We just want it to be able to discover these are all of the devices in this environment. The exporter endpoints, so those endpoints that run within a service, we wanted those to be self-service from an engineering point of view. So we didn't want to have to be in a situation where, oh, excuse me SRE, excuse me ops, could you please add my exporter endpoint to the configuration? Engineers should be able to just add a line of configuration when they deploy their service, and we will discover that it lives. TLS encryption of everything, like that's a non-negotiable at Fastly for pretty much everything. And we wanted minimal exposure of those TCP ports. So if you think about the sort of that deployment model where you have many services running on a machine, each one of those has its own exporter endpoint, you could end up with anywhere 15, 20, 30 different TCP ports that may need to be open on that host. We didn't want to do that, just to reduce the surface area of what's exposed on an individual machine. And the way all of these components, going back to that diagram, sort of interact is we have the sidecar queries each individual device through the proxy to find out what services do you have, what could I scrape, what juicy information do you have for me. The sidecar's other responsibility is to generate the configuration for Prometheus. So the configuration that's generated is telling Prometheus, now that we know all of the things that we can scrape, how do we put that all together and wire it into Prometheus itself? And then Prometheus scrapes those targets over TLS through the proxy. So we sort of complete this loop here. So getting into a bit more detail on the PromSD. So PromSD is our internal name for this this service discovery mechanism, because simple names are good. So the first thing that it does, the sidecar, so we have a system called Configly, which is our internal global runtime configuration system. So every service within Fastly is configured, has all of its configuration properties living in Configly. That's integrated with Chef and integrated with all of our other systems. So it's like the global view of our configuration. So it queries Configly and says, hey, what hosts do you have in this data center? Returns a list of IP addresses. The sidecar then goes, for each of those individual addresses, goes and hits a target's endpoint, which is one side of the proxy that runs on every machine. And that returns a list of, these are all of the services. For my IP address, these are all of the services that you could scrape for metrics. It then takes those two sources of information and generates what's known as Prometheus has a file service discovery mechanism. So you can generate a file in this format and Prometheus can dynamically load that when it changes, and that will do all of the configuration for you. So if you ever need to do any integration and there isn't a native integration, this is a really easy way to do it. And from that configuration file, Prometheus reads that in, and then that's your configuration. So rather than having to statically generate your Prometheus YAML config file from Chef or anything like that, you can just generate this file dynamically using an external process. And there's a couple of blog posts around recently of some other folks that have built some examples around this for other systems. So that's the sidecar component, runs on the Prometheus server itself. It's responsible for doing all of the configuration for us. Now the proxy, which runs on all of our individual hosts, it's responsible for a couple of things. So the first thing the proxy does, and I think there's no way of getting around it anymore. Systemd is here, and you just kind of got to embrace the overlords. And so what the proxy does is it makes a dbus query to systemd and says, tell me about all of the services that you have enabled on this machine. So every service that we deploy runs as a systemd unit. It's able to pull back a list of all of the units that are installed, set up, and configured on this machine. It takes that list of services and then talks to Configly again. So in Configly, every service that's deployed on a machine has all of its runtime properties stored in our back-end configuration system. And what we did is we added an additional key as part of the standard configuration, just called the Prometheus properties, which describe where the exporter lives on the machine. So if you're running a service and you expose port 1234, and that's what you'll hit for your metrics, that's what you describe there. So if I'm an engineer deploying a new service and I'm exposing metrics on a particular TCP port or a Unix domain socket, I just list it as a target there. And then the PromSD proxy takes those two bits of information, does a little bit of mashing together, and exposes two endpoints. One is the /targets endpoint we talked about previously, which the sidecar hits, which obtains a list of all of the available metrics endpoints on the machine. And then the second one are our proxied paths themselves. So we construct a particular URI scheme. In this case, it's like service name _ port /metrics. And that literally is just as if you were doing regular reverse proxying. That maps, so the node exporter one maps exactly to the local host 9100 port. So that's sort of the magic of how we kind of have locally running exporters, but we expose them externally off this one service. So that's the proxy part. This is probably really bad after a few deliriums. So the good part was it worked. Now that service is a couple of hundred lines of Go. It's not particularly complicated or fancy by any stretch. So yeah, worked really well. The things we learned from that was it's really easy to leverage the file service discovery mechanism for whatever purpose you might want to do. So you're not limited to kind of building your own system. Like you could generate a file with Chef, you could write your own little process that talks to whatever system it needs to generate that file for you. And then you get the benefits of dynamic configuration for Prometheus. New targets for engineers are really easy to add with a single line of config. So they just have to add that Prometheus properties part in, and it magically just works. We have TLS and authentication everywhere. Yes. And we have a single exporter port open on every host. So rather than having those 20 or 30 ports open, we have this single port that has access to all of the metrics and all of the services exporting metrics on it, which is a little bit of a double-edged sword because if the proxy falls over, and occasionally we've had a few dbus issues, all of your metrics will stop being exported at that point, which also is a good proxy for the hostess down. But that's like a trade-off at this point. It hasn't been too much of a problem. So now that we've done all this work, we've built out our infrastructure, we've built this service discovery mechanism, engineers are onboarded, we've set up our exporter endpoints. How's the adoption been? So as of a few weeks ago, some of the numbers of our scale at Fastly with our Prometheus infrastructure is we're running 114 Prometheus servers. So around the globe, we have 114 individual hosts that are operating on the infrastructure. Those hosts are storing about 28 million time series, which is pretty reasonable. And at any given time, we're sampling about 2.2 million events per second. So sampling all of the different endpoints for metrics. And that's just growing. We're about, as I said, about 80% through. So yeah, it's been fantastic. So trying to meet those goals of is it easy to deploy? Yes. Is it easy to operate? Hell yes. Does it scale? Sure does. It's great. Like an individual Prometheus server, the current sort of benchmark stat is an individual server can do about 5 million metrics or 5 million samples per second. And we're doing, we have so much headroom, it's not funny, which is great because the deployment, if you have some spare hardware lying around, you can just run it. Doesn't need big machines. And the wins for the company were that engineers love it. So the instrumentation libraries are super easy to use. Engineers kind of have really gotten on board with the ability to instrument their applications, how easy it is to run Prometheus. Given that you can run Prometheus as a single binary in all of the development environments now, they will run their own Prometheus instance, so they can scrape their own metrics as they're developing. They can build dashboards locally with Grafana. Try doing that with Graphite, and that would be really fun. The dashboard and alert quality have increased. So now that we've kind of reinvigorated the culture to get everyone kind of on board on like what makes a good dashboard, what makes a good alert, the quality. So we have a much lower false positive rate. Engineers are really empowered to make sure that their systems are observable, that the alerts make sense, that they're going to the right people. So that's been fantastic. The PromQL language, which is the query language for Prometheus, it's incredibly powerful. Yeah, absolutely love it. The amount of crazy stuff you can do with it's really cool. From a scaling perspective, the Prometheus infrastructure, because we're stamping out multiple Prometheus instances per POP, it scales with our infrastructure. As we roll out more POPs, our Prometheus infrastructure grows, so that's been absolutely fantastic. But there's still some rough edges. One of the biggest ones is exploring metrics when you have no prior knowledge. So we've kind of dubbed this breadth-first search. So if you think of the scenario where I have two hosts in a POP, one host is doing what it should, the other host is doing something weird. How do you figure out what's going wrong if you don't already have alerts that have alerted you to that, like weird emergent bugs? So with the systems like Ganglia that do server-side rendering, it's possible to render 2,000 graphs on a single page and just zip through with a scroll wheel and look for the ones that look weird. And that's a debugging methodology that still gets used a fair bit at Fastly. For better or worse, but there's no real other way to do it because with all of the client-side rendering that we have now, you can't realistically download hundreds of megabytes of JSON and deserialize it and then render that all in your laptop unless you like watching Chrome crash. And this applies to not only Grafana but also to a lot of the SaaS products, being able to present these huge slabs of data. People still want to be able to do it. So we've done some prototype work around some server-side rendering for Prometheus to be able to do that kind of thing. Alert Manager is an amazingly powerful tool, and I think the only downfall is that it's too flexible. The expressiveness that you have for configuring alert routing trees and things like that can get really gnarly when you have a multi-tenant environment. So we consider our environment multi-tenant in that we have multiple, like dozens of service teams, and they're in full control of how their alerts work. So there are potentially sharp edges in Alert Manager configuration where one team can potentially impact another team's alerts. So we've had to kind of put guardrails around that, which makes it a bit tricky. This one is probably the biggest hot button, I think, for anyone who's rolled out Prometheus at scale, is that because you have all the metrics stored in individual sites, getting a global view is really hard. So federation is a kind of a way to do that, in that you federate a subset of metrics at a global level. But usually what happens is you will have an engineer come to you and say, do you have this metric federated? And it's like, no. And usually when they ask that question, they want to see it sometime in the past. It's like, we can do it from now on, but we can't go back in time. So that's a little bit of a problem. Projects like Thanos are super promising. If anyone has rolled out Thanos in production at a reasonable scale and it works, please come and talk to me, because I'd love to pick your brain about it. Yeah, Thanos looks fantastic for this purpose and would solve a lot of the problems, so we're looking at that. And following on from that, the long-term storage is still an open question. So when we started the project, we made it very clear that one of the service level objectives of the system was to be real-time operational telemetry. We're not trying to store 5 years of data. Our sort of promise to the company was we'll store between 60 to 90 days of metrics online at a time. And if there is a need to store some metrics for a longer period, like, we'll take that on as a separate project. And I think there is definitely some room to think about the problem space of storing sort of your real-time I need to know now metrics versus I need to have a system to store metrics over time for trending. Because I think they're two separate problems, and most of the systems that have tried to do it all have kind of fallen down on one or the other. So in summary, because I'm out of time, Fastly loves Prometheus. It is absolutely amazing system. The project's been hugely successful, and we're in really good shape now. So thanks. We done? No time?
Yeah, we've got a few minutes.
Okay, I can take a few questions. Anyone? Yes, down the front. Oh, okay, yeah. So the question was, what was the alerting system we had before and how are we doing it now in Prometheus land? So in our original Ganglia system, and also with our SaaS provider, we used the SaaS provider's native alerting originally. And for Ganglia, so Ganglia just stores all the metrics. We were running Isinga for writing all the checks, so it's essentially just Nagios. And we had a sort of a check Ganglia check sort of program that we would run, and you would just run that against a metric and say, oh, if this value is greater than a threshold or lower than a threshold, throw an alert. So on the Ganglia side, it was basically Nagios querying Ganglia for metrics and alerting off thresholds. For Prometheus, which I didn't cover off there, there's another component in the Prometheus ecosystem called the Alert Manager. And what the Alert Manager does is it's a separate daemon that you can run multiple of, and they mesh, talk to each other over gossip. And each Prometheus instance, when you configure an alert, so you sort of create a query, give it a sort of a condition, so you would say something like request per second less than 100. When that condition's met, each time it does an evaluation, it will then emit, just over a HTTP protocol, it will emit to the Alert Manager an event saying, oh, this condition is failing, and then Alert Manager takes care of routing it to Slack or to PagerDuty or anything like that. So Alert Manager is what you want to look at. You can find that on the Prometheus docs site. Yep. Anyone else? No? Oh, over here. No. Yes? You were describing your PhD setup. Yep. Yeah, so what we do there is if we lose one, and I had another slide, I don't know where it went, showing the HA. So our Nginx reverse proxy, we just have an upstream configured with a primary and a failover. So when the A side falls over, we route to the B. If we need to recover, so say that the A host is a molten pile of metal at this point, we roll out a new machine, spin up some new disks, we just async the data from the B to the A. Yeah, it's nothing more fancy than that. It works great. There are a couple of caveats around that, depending on how you're doing some alerting, because you'll have metrics on there that may have been generated by the host itself, and now it appears that it's not collecting those anymore because those metrics don't exist. But the actual underlying time series database format that Prometheus uses is very similar to systems like Cassandra, where you have this write-ahead log, the live metrics are coming in, they're getting updated live. When you hit a certain threshold, which I think it's about 2 hours, it rolls those out into read-only data files. So you can just pick those up and copy them across. And the wall will just repair itself if you spin it up on another machine.
So I think we have time for one more question. We're going to go with the patient person over there in the blue shirt.
Okay, so one project that may interest you, so people don't step on each other's toes with alerting is Alert App.
Oh.
It's like an alerting app that can further decide what to do. And a question, will those sidecars, so that proxy on the exporters and the discovery mechanism on Prometheus side, will they be open source?
We're thinking about it. There's a lot of, they're relatively simple. What we've sort of talked about is open sourcing like an example of it, because unless you're using our configuration system, it doesn't really make sense. And like if we go and abstract that out to be pluggable, maybe. But yeah, maybe is the answer. Sorry.
Thank you.
No worries. All right, I think we're done.
All right.
Thanks,
That's it.
everyone.
Thank you very much.